Free body diagrams played a big role in University Physics 1. So for this course overview problem, I thought I'd choose a incline that's fixed and rough. It's got a kinetic and a static coefficient of friction. A very heavy block of mass 8m is on it, and attached to it by a string passing over a massive pulley is a cylindrical mass of mass m. The pulley itself is massive, which means that we have to take into account the rotational ideas that we learned in the course as well, specifically the moment of inertia and Newton's second law for rotation. So this problem has got two parts. What are we trying to find here? We're going to first address if the system is going to stop. Does 8m stop? Because remember, it's moving, it's said to be moving initially in the upward direction. So does it stop? It might seem plausible for it to stop because 8m might easily overwhelm 2m and m. So that's the first part of the problem. The second one is, does it move again? Turns out to be two separate issues, so let's tackle them one by one. The first order of business in any second law problem is to follow the process of drawing the free body diagram. Now I'll be a little informal here and draw the free body diagrams right where they happen. I'll call this attention T1, so that's going to be T1 also by the Newton's third law. Now if it's going to stop, the acceleration direction has to be opposite that of the velocity. So to answer that first question, let's take the acceleration to be opposite the velocity, and then if it does stop, the acceleration will be bigger than 0 as drawn. Because the string is not stretching, this is also going to go up the same way, and the pulley is going to accelerate with an angular acceleration alpha that's consistent with the direction of A, and that direction is out of the page or positive because it's counterclockwise, and this is down. I'll take this to be the x-axis and the y-axis to be that. I always like to take the y-axis to be positive in the direction of acceleration for these vertical masses. And then we're not done yet. The tension, because acceleration is in this direction, we need tension T2 to be smaller than the tension T1. That's T2 again, and this mass is the smallest force. The weight is the smallest force there because the whole thing has to accelerate up. We can write Newton's second law for translation and rotation next. Sum of all the forces in the y direction equals mass times acceleration. For the cylindrical mass, I'm going to get T2 minus mg equals ma. Let me call that the first equation. Then I have the rotational equation for the pulley by Newton's second law for rotation, that sum of all the torques about the center of mass equal to the moment of inertia of the pulley about the center of mass times the angular acceleration alpha. Now here I want to note that alpha is related to A by the no slip condition. So alpha equals A divided by R. Let's just make a note of that because the string does not slip over the pulley. Let's write the sum of all the torques. Torque is R cross F. In this case, it's the radius times the force times the sine of the angle, which is 90 degrees. And that's a positive torque because it's counterclockwise. That's a negative torque because it's clockwise. So we can write the signs for those torques. T1R sine 90 degrees minus T2R sine 90 degrees. Now I haven't told you what the pulley is made up of. Let's assume that it's a disk. So a disk has got a standard result, 1/2 mr squared, where m is the mass of the pulley. In this case, it's 2m r squared times alpha. Alpha is a over r, so that's just a over r. Observe that the r cancels out and another r cancels out like this. So you did not need to know the radius of the pulley, which in fact I did not tell you anything. So that's a good thing. I get T1 minus T2 equals The half cancels with the 2, so I just get m times a. That's the second equation. The last equation is one pertaining to the x motion and the y motion of the 8m block. Now the 8m block is not accelerating in the y direction, so sum of all the forces in the y direction equal to 0 for that block tells me that, let me complete my free body diagram for this one. That's going to be the normal force. Gravity would act straight down, but the component of gravity in the direction of the normal force is 8m g cosine theta, and the component that's in this direction is 8mg sine theta. Now because it's initially moving up, the force of kinetic friction must act down, so that's the force of kinetic friction, FFK. All right, so we are back in business. That's going to be Fn equals 8mg cosine theta, and then we can use that. The law of friction is force of kinetic friction equals mu kinetic times the normal force, so that's 8mg cosine theta. Well, with that behind us, we can write the equation for this mass. It's going to be sum of all the forces equals max. Well, acceleration promoting forces are 8mg sine theta plus the force of kinetic friction, which is mu kinetic times 8mg cosine theta, minus the tension, because tension is acting against the direction of acceleration, equals the mass 8m times the acceleration. And I think I can make one more simplification before calling it equation 3. So I can take 8mg outside common, and then I get sine theta plus mu kinetic cosine theta minus T1 equals 8ma. To solve the first part of the problem, I need to figure out if acceleration is bigger than 0. If that's the case, then it'll stop because acceleration and velocity are fighting each other. So let's solve for the acceleration. What you don't need is other tensions. So if you observe these three equations, they have tensions with opposite signs. So adding them may be a good strategy. Let's do just that. 1 plus 2 plus 3. I'll put them one below the other. T2 minus mg equals ma. T1 minus T2 equals ma. And then 8mg sine theta plus mu kinetic cosine theta minus T1 equals 8ma. When I add them, the right hand side is just 8 plus 2, 10. These cancel out, and I just have here 8mg sine theta plus mu kinetic cosine theta minus mg. M also cancels from both sides. And finally, the acceleration is the whole thing divided by 10. Acceleration is g over 10. And then I'll finally put what theta is. Theta is half, so that's half plus mu kinetic, which I said was 0.3. Cosine 30 is root 3 over 2 minus 1. So that's going to be g over 10. 8 divided by 2 is 4, minus 1 is 3, plus 8 times 0.3 is 2.4 divided by 2 is 1.2. Well, basically it's bigger than 0. So indeed, 8m stops. So the answer to the first question is yes. To answer the second question, we cannot rely on the free body diagram we drew earlier because that assumed that the system was moving. Now this asks us, after it stops, will it move again? In other words, when it stops, you're introducing a new source of friction, which is a static friction. will that static friction be enough to hold everything in place and keep the mass 8m from dragging the whole system down? Remember, the bias of 8m is to slow the system down. So after stopping, there is a very good chance that because 8m is so much bigger than 2m and m, it'll go down. Well, is static friction enough to stop that? Let's draw a separate free body diagram to analyze this part. So I'll draw the system again. Because it stopped, the nature of the free body diagram itself completely changes. Now remember, this is jonesing to go down. So we have to have the force of static friction. The maximum value of the force of static friction is what we need to use to make sure that it just is about to break free. And there's a tension T. I will no longer call this T1 and T2 because if this is not moving, the tension T has to be the same throughout. The tension T is actually equal to mg by just examining the cylinder. The pulley is not going anywhere, so that's T and T, keeping the pulley still. And that T again acts up on this block along with F sub Fs max. And what's the possible engine that could drive this whole thing down would be 8 mg sine theta. So the big question we have to examine is 8 mg sine theta bigger than FFS max plus T? If that is the case, then you will have movement again. So let's write that. For movement, require that 8 mg sine theta be bigger than the tension T plus the maximum force of static friction. Let's talk about the static friction for a moment. The force of static friction, unfortunately, is not as simple as the force of kinetic friction. It's less than or equal to mu static times the normal force. However, when you're maximizing it, that's when you have to choose the equal sign instead of the less than or equal to sign. So then you can use a result similar to that. The normal force is always 8 mg cosine theta because the block does not fly up or down. So I'm really getting informal about these free body diagrams. Usually happens to me at the end of the course. In the beginning of the course I did force tables and all that, and now I'm not doing any of that. Anyway, so we have here everything we need to answer the question, and T is equal to mg here because this is not accelerating. 8 mg sine theta is it bigger or not than tension, which is mg, plus 8 mg times mu s cosine theta. Mg cancels out. So we have to ask if 8 times sine theta, which is half, is bigger than, that's the 1, plus 8 times mu s, which I chose to be half, times cosine theta. Mu s is half, just to remind you. Cosine theta is root 3 over 2. I'm sensing a problem here. So 4 is 4 bigger than 1 plus 2 root 3? I don't think so. Let's see. I'm asking if root 3 is 1.732. 1.732 times 2 is 3.4 and change. So that's going to be something like 4.4 plus. No. So this is not going to move again. The answer to the second question is no. It is stuck there. So even though it was 8 m, it is unable to drag the whole system down after it stops momentarily. That's a pretty surprising result.